Now let us go to the properties of tensors, algebraic operations of tensors. Look at this. If T ijkl dot, I think you can understand what this is. This is a tensor of higher order rank, that is nth rank. You can generalize it n, tensor of order n, and u suffix ijkl etc. That means this is another tensor of order n. If these two are two tensors of same order, then you can add them. You can add the tensors. If you get two tensors of same order, you can add them. You will get another tensor of same order. That means if you add two tensors of order 2, then you will get another new tensor with same order 2. So algebraic operations, addition is possible with tensor. Subtraction is also possible with tensors. Product rule. If a tensor is multiplied by a scalar, then the result is a tensor of the same type. Just number you are multiplying, so magnitude alone changes, and the tensor, it remains, the type of the tensor remains the same, its order will remain the same. This is called the product rule. Can I move?
Yes, ma'am.
What is this? Direct product. I think this is hiding to me. Is it hiding to you also? Is anything hiding the screen?
No, ma'am.
Okay, then okay. This is direct product. If a tensor of rank R is multiplied by tensor of rank K, then the resultant will be a tensor of rank R plus K. Just a minute. Hello. Accept. Okay, doctor. I'm class முடிச்சிருவேன். Okay, right. Thank you. I'm sorry. Actually, an interview is going on for the hospital. Some temporary nurses and doctors we are recruiting, and the interview is going on. So parallelly, I have to work for that also. But I want to finish this. Okay, coming back here. If a tensor of rank R is multiplied by a tensor of rank K, then the resultant will be a tensor of rank R plus K. If I think you understand, you need to just add the ranks of the two tensors like this. I explained this with an example. I have taken ordinary vector, and you know now vector is a tensor of order 1. So here I have taken a vector which is a tensor of order 1. Now I am taking another vector which is a tensor of order 1. Another vector of order 1. Now I am taking direct product. And I think you heard of this direct product. Already you have seen only dot product or cross product between the vectors, right? But when it comes to tensors, there is another kind of multiplication which is called a direct product. Direct product. There is no dot or cross in between. You can straight away take the multiplication. So this vector and another vector. Actually, in here we need to speak in terms of tensors. This tensor of rank 1 is multiplied with another tensor of rank 1. This is direct product. That means, and the symbol of direct product is this. You have to put across encircled by a circle. This is the symbol for direct product. This is how you have to expand the product. Like how you normally take the product with ordinary terms. If you have 3 terms multiplied to another set of 3 terms, how you do? The first term will be multiplied to the first term of the second system. Similarly, the first one will be multiplied with the second term. First one will be multiplied to the third one of the next term. Likewise, you do second term with the first. The same thing. A1, B1, I cap into I cap. So A1, B1, I cap, you just simply write. without putting any dot or cross between. And A1, B2, so A1, B2, I and J, so I and J, plus A1, B3, I and K. Likewise, you take all the 9 components you get. This is direct product. This is possible with the tensor. But when it comes to vector calculus and all, we won't do it. In vector calculus, dot and cross only we will take. But after knowing tensor, you will come across this kind of product also. This is simply multiplying and writing. Because now you know 2 directions also can be involved in an entity. Just before you have seen stress component which involved 2 directions, right? Represented by x and y like that. Here we are representing the similar thing in terms of unit vectors. So 2, we can have some physical entity which can be represented by 2 directions, and in higher order tensors, they can even be any number of vectors, I, j, k, like that, any number can come. So don't be surprised if you see when I write like this. So this direct product of 2 tensors, in our case, it has given 9 components, right?
Yes, ma'am.
Okay. So here, if you look at the component here, you can generalize. You can write it like A, B, and 2 vector components you can write. But can you tell me the order of this tensor now? It includes 2 directions, right? So its order is 2. It must be a dyadic. It must be a dyadic. Now its order has turned into 2. Already what you used was a tensor of rank 1, and that was multiplied by another tensor of rank 1. So what is the product? It is a tensor of order 2, because now this can be written in the form of a matrix also. 9 components are there. You can write in the form of matrix, and it involves 2 directions. So it defines a tensor of rank 2. So the product, after taking a direct product, you get a tensor of rank order of the first tensor added with order of the second tensor, right? This is an example I have given, but if you do it for higher order tensors also, what you get, it will be the sum of the orders of the tensors you used. See, if you take a direct product between these 2 tensors, each of order 1, the result will be a new tensor of order 2. That is what we have got here in our previous case also. See here, this is one tensor Tmn. I told you this mn is written here as prefix, and here it is written it as a suffix. We will come to know the names of them later. You can write this anywhere as prefix or suffix. Both are the same. Just a minute. Hello, Muthukrishnan. இங்கே தான் என் ரூமில் தான் இருக்கேன் முத்துகிருஷ்ணன். Right, thanks. Okay, so if you take a direct product between these 2 tensors, you see from the prefix or suffix you can understand this is a tensor of order 2, this is another tensor of order 2. So the answer should be a tensor of order 2 plus 2, 4. So mnij or suffix mnij. This is an example for direct product. Shall I move?
Yes, ma'am.
Contraction theorem. Contraction of a tensor of rank R always results in another tensor of rank R2. This is R minus 2. This is an important theorem, another important theorem in tensor. Contraction of a tensor of rank R results in another tensor of rank R minus 2. What is contraction first of all? Contraction is introduction of a dot, meaning dot product. Introduction of dot in between any of the elements involved. If 2 tensors are involved, then introducing a dot. For example, UVW I have taken. In our example, UVW are the vectors. That means tensor of order 1. each. U, V, W. Now, you do an operation called contraction. In tensors, this operation is allowed. That means incorporating a dot product. In between U and V, I am doing contraction process. I involve dot product between this one. So U dot V, it is going to give you a scalar, isn't it? Because though they are the tensors, they are nothing but the vectors. So since the order is 1, so it's going to give you a scalar. So I have taken it as K. U dot V, now it has given a scalar. The scalar into this vector. Now tell me, what is the rank of this tensor?
And
This
that's
is
a zero rank tensor. K.
This is a tensor of order 1. Yeah, scalar has order 0. This one has order 1. So totally it has become a tensor of order 1. Right? So what happened here? U, V, W, each of them are tensors of order 1. When you take a direct product, you add the tensors. So 1 plus 1 plus 1. So in left hand side, if you take a tensor, the order, the rank of this was 3. But now what happened after involving the contraction process, it has become single vector, a scalar multiplied by a vector. So here 0 plus 1 only. So it is 1. What happened? 3 has become 1. What happened to the rank? It is reduced by 2. Isn't it? You understand? Here it is direct product. U, V, W, direct product. So here if you find the tensor totally, the rank of the tensor totally, tensor of this one, just before we have seen in the previous slide, we have seen for direct product, the tensor you have to add up. You remember? So in the left hand side, 1 plus 1 plus 1, you have the rank 3. But after incorporating this contraction, after incorporating the dot product, now it has become W. Or after multiplying this K inside, it is going to be some vector. A vector is nothing but a tensor of order 1. So here after contraction, its tensor has reduced to 1 from 3. 3 to 1 means it is reduced by 2. That is what this contraction theorem says. Whenever you apply contraction to a tensor of rank R, you will end up with a new tensor with rank R minus 2. You got it?
Yes, ma'am.
Yes, ma'am.
Okay. Types of tensors. Now, I told you some of the tensors had prefixes, some of the tensors had suffixes. See, suppose you are dealing with the tensor of rank 10. Tensor of rank 10. That means how many suffixes you have to write?
And 10 surfaces.
10 suffixes needed. For example, the tensor is T. T is the tensor. And below, as a suffix, you have to write A, B, C, D, E, F, G, H. Up to 10 you have to write. Okay. So it will take a long space. It will occupy a long space if you write continuously like this. So what we do, we split. We can write few variables as a suffix and few other as prefix also. So both are possible. So you can have them as upper indices also. So this kind of convention also has come. It is your wish. If you want to write the suffix, you can use, or if you want to use the prefix, you can go. We normally use the words upper indices and lower indices, index those numbers, upper and lower indices. If you prefer to write only the upper indices, we name the tensors as contravariant tensors. Contravariant tensors are the tensors having only the upper indices. Example, Tm, Aij. Covariant tensors. If you prefer to write...
Ma'am, how does the contravariant tensor solve our problem of writing the suffixes so long?
No, here I am just a mixed variable. See, this kind of things solve this kind of part. Whichever disadvantage I told you, like writing a long suffixes, you can, instead of writing all the four at the bottom, you can split and write as the top also. So they brought into the conventions of different types of sensors. Either you can write on the top or you can write as the lower indices. If you prefer to write only the lower indices, they are called covariant tensors. If you prefer to write only the upper indices, they are named as contravariant tensors. But you can prefer to write in both upper and lower indices. For higher order tensors, if you are going for only covariant or contravariant, it is very uncomfortable to write long indices. So mixed tensors were introduced.
And ma'am, one last question, ma'am.
Yes.
These contravariant and covariant don't have any physical significance, right? Until
They don't have much differences. You can write anyways.
okay, ma'am. Okay.
T with upper suffix, T with lower suffix, both are the same. Unless you define their limits, for example Tm, and if you are writing m is equal to 1 to 4, if you are writing Tm, T suffix m, and if you are defining it as m is equal to 1 to 6, if you make some variations and you have to describe it earlier, otherwise they are the same with limits.
Okay.
Suppose you want to make the difference, contravariant and covariant tensor, you are using the same notations like T upper index m, T lower index m. If you want to make the difference, you have to describe it. Only difference you can make is with the limits of m. But you have to describe it in the introduction. Got it?
Yes, ma'am.
Okay. So mixed tensors. So mixed tensors can be like this. You can make the upper indices and the lower indices, and totally for this the rank is 4. Right? Here also the rank is 4. You can split